Hello, everyone. We can, let me introduce you. The speaker of today is Duong, and he's gonna talk us about quantum neural architecture search with quantum circuit metric and Bayesian optimization. He's an intern with me and Patrick in the fourth floor from Gaussian Institute of Technology. So please go ahead.
Okay. Hi everyone. Today I'm gonna bring you my reverse work on quantum neural architecture search. Probably you all know about neural network, and we translate it into quantum neural network by replacing the layers by quantum gates. So the problem is how to find a good architecture that works for a problem that you don't have a prior knowledge before. So there are a lot of, not really a lot of, there are a couple of attempts have been done for the problem for the QNAS quantum neural architecture search. So there are two types of them. The first one results on several quantum properties. Some of them are cell-based search or adaptive answers, but the limitation of the first approach, they usually require a very restrictive structure of the quantum neural network, or usually they're also called answers. So basically they are kind of similar things. And the second approach is borrows their adaptations from the classical neural architecture search. The problem with the second class of the second approach is that they usually provide little insight from the quantum field, but rather just directly applying a well-known techniques from classical neural architecture search to the case of quantum machine learning. Okay, so we propose another algorithm for quantum neural architecture search, but now we're using Bayesian optimization. But the main contribution, however, is two metrics, is two distant metrics. The first one is a metric between quantum gates, possibly parameterized, and the second one is a metric between quantum neural network architectures. Those are independent to the Bayesian optimization, so that might find applications beyond architecture search problems.
Sorry, what is neural architecture search?
What is neural architecture search?
Search, yeah, I know neural network.
Yeah, I will explain in the next slide. So here you will see the general structure of a quantum neural network. So every quantum operator can be represented by a unitary. So in our case, the unitary U here is a sequence of fixed and parameterized unitary. So parameterized is U, UI, from U1 to UL, and fixed gate is W1 to WL. And the architecture search problem is whether how should we specify UL and UI and WI in the sequence. We can train the parameters from a lot of optimization algorithms, for example, gradient descent. But usually the architecture which is the factor that determine how good your machine learning model is. So we have several components here, and we have to choose which gate from this collection. Here we use two common set of gates. The first one, fixed gate from the Hadamard gate, control poly, and poly gate. For parameterized gate, we have rotation gates about 3-axis and the double rotation. So these 6 gates are 1 parameter. So we limit the problem into 1 parameter gate. So, and the core idea of Bayesian optimization is that the Bayesian optimization is a global optimization algorithm. So in essence, it models a function by a Gaussian process. Gaussian process is a random process that any finite number of random variable taken from that Gaussian process, they form a Gaussian vector. So it means they together follow a joint normal distribution. We can fit the function f(x) here is can be, in our case, is a measure of a performance with respect to any learning task you want. X is a neural network architecture, and Y is the performance of that architecture under some training task. So suppose we have a training data, a lot of architectures, and we train it, we got corresponding performance. We fit into the Gaussian process by maximizing this likelihood. And after that, we can compute the posterior normal distribution. Of course, it's a normal distribution, and the posterior mean and covariance can be evaluated from this. And this is the Gaussian process part, and the Bayesian optimization is the process of selecting new sample points. The sample points here are the new architectures. So we choose new sample points from the fitted Gaussian process by maximizing an acquisition function called expected improvement. The expected improvement is the average improvement of a new sample point over the current optimal point. So we maximize this function using, for example, evolutionary algorithms. So the building block.
What is M and K? Is like small k is a kernel or
big K?
Yeah.
The big K is the function, a kernel function. So we specify the kernel in the next slide. It's the most important part in the whole Bayesian optimization part. And then the big K is like it's a matrix computed from the small k.
And M?
And it's a mean function for the Gaussian process. It's like the mean function of x given beta big X.
The F star.
F star is the last maximum point. Suppose we are at stack t, and at t minus 1 star is the largest y from from y1 to yt, from y1 to yt minus 1, and the best performance so far.
You cannot evaluate the f of x of just the F star.
This is from the training set.
But the f of x you cannot.
Yeah. We cannot compute y. It's expensive to compute y. So we rather model y by fx, and fx is the Gaussian process, and this function will be computed based on the mean and the posterior mean and the posterior variance, and it's quite cheap to for the evaluation. It's quick.
This is like your figure of merit that you are trying to optimize.
I'm sorry.
This is like your figure of merit that you are.
Yeah. The Gaussian process is a surrogate model. We use the surrogate model to to maximize its expected improvement, not exactly using y here. No. And the most important part, as I told you, is the kernel function. Usually, a kernel is like a similarity measure. It can be, and it usually is constructed from a distance. For example, you know the Gaussian kernel is e to the minus distance square, and in our case, we define the kernel by defines the form of exponential of minus distance of negative distance. So it has the same form to the Laplacian kernel, but in the Laplacian kernel, the distance is Euclidean, but in our case, the distance is a metric, but not Euclidean, so it's not exactly the same to Laplacian, but has the same form. Oh, all right, and so our goal now is to define a distance function between two quantum neural networks. Suppose this is P1 and G2, they are two networks, and we have to compute the distance. It should be noted that the architecture, they don't contain the parameter yet, so it's just the architectures. And in order to do that, we specify these three ingredients. The first one, the gate mass. This is the amount of computation that a gate can perform. The second one, the gate type mismatch, is the difference between two gates. And the last one, the structural distance, the similarity is the difference in terms of topological position of each gate in their respective quantum neural network. We come to the first ingredient, gate mass. So, as you know, a unitary matrix of size p times p has p minus 1 real degrees of freedom. So we define the gate mass for a parameterized gate by the number of parameters it has times p minus 1, p squared minus 1. And for fixed gate, for fixed gate, we can imagine fixed gates are an analogy, similar to activation function in a classical neural network. So the power of activation function, they depend on the power of trainable layers. So here we define the gate mass for fixed gate as a fraction of the sum of gate mass for parameterized gate. And the total mass, of course, the sum of every gate mass in the neural network. And the second ingredient is the gate type mismatch. Here's come the first metric, the metric between quantum gates. So consider a quantum gate. It can be fixed or parameterized, or in our case, parameterized by one parameter. And the exact effect of the gates can be different depending on the definition, but they can generate kind of the same shape. For example, you see the rotation about the z and rotation about the x-axis. They are different, but with the pattern they produce over the entire Hilbert space. Here is the log sphere, is the circle. It's always the circle. Whatever the state you are applying on, it generates a circle. So intuitively, they have the same shape. We call it shape. Rx and Z have the same shape. And you can see from the last figure, Z, X, and the superscript X, the superscript is the oscillation direction. So ZX is the rotation about the Z-axis, but with small fluctuation around the X-axis. So these two gates also have the same shape because you can imagine we can rotate the red line in mapping exactly into the blue line when the orbit can be matched exactly with, say, the two gates have the same shape. And that is the problem of the shape. And for the exact definition, it should be accounted by the coordinate. So the coordinate, for example, here is will quantify the difference between the rotation direction here z and x, and so the coordinate will consider the difference between the rotation direction between the two unitary.
Sorry. Is this a distance?
Is it a distance? Yeah, I will discuss that later. I can show that this is a distance.
Then this shape.
Hmm?
I can understand it like in theory, but higher dimension, no. Literally, I understand the shape, but not mathematically.
Yeah, I will explain mathematically later in the next slide. Okay, first, the coordinate is simple because in our set of predefined gates, we can always specify a unitary by a fixed Hamiltonian. So the coordinate is the distance, is the nuclear distance between two generating Hamiltonians of our gate. Suppose the Hamiltonians are normalized to have one nuclear norm. So it's obvious that the coordinate is a metric because it's a norm-based distance, so it's a metric. And the second part of this is about the shape distance. So imagine we have a z and rx. The two gates are said to have the same shape whenever we apply, for example, the first gate to a state psi, then there is a corresponding state phi that will apply that U2 acting on will have they generate the same pattern, but we want to match these two patterns together to fix it as close as possible, and the matching term will be V. So here for any state sign, the two gates are said to have the same shape if there is a counterpart phi and V such that this is true for all parameters theta. And if we integrate the whole thing, then we get this one, the integral over the Hilbert space. And so of course it's reasonable to define the shape distance by 1 minus this thing. That is the integral over the Hilbert space, so we have to approximate the integral.
Phi is depending on theta, P, the counterpart state.
Yeah.
Is it depending on theta?
Yeah, it's dependent on theta. No, I'm sorry. It's dependent on sine, not theta, It's there should be a fixed V for every side, and for every side there is a corresponding phi sine. Phi is a function of sine.
For any the same one.
Yeah, for any theta, the same V, but different phi.
So phi is depending on theta.
Phi. Phi depend on sine. I'm sorry. Phi depend on sine. Phi depend on sine.
Integral is over the parameter of the circuit and the set of pure states.
Yeah, integral over the set of theta and the set of state.
You say there is a fixed unitary V, so you fix V according to the value of psi itself as well.
Like each side would carry its own V?
Yeah. So, because this equation should be true for every side, so the V here is independent of side. So this V is rather a function of U1 and U2, not just state outcome. But phi is dependent on side.
Okay, so when you perform the integral, then you also change phi, no? In the integral, when you change the sign, you also change phi.
Yeah, that's right. If you see here, and for example, the circle around the blue circle around the z-axis and the red circle around the x-axis. So the blue circle is like you rotate x, you stay plus x around the z-axis, and here you rotate the state 0 around the x-axis. So suppose x is a sine, then here we have a corresponding phi. But if we take another initial point, for example, a point next to x here, so and the corresponding phi should be close to something here. But the matching V is the same because the matching V is to just try to match the whole circle, not a single point, because it should be true for every theta. So it's true for whole circle to match. I mean, it match the true circle line by line, point by point. Sorry.
So maybe you can write phi and then on parentheses side.
Yeah, it should be.
Okay.
Yeah. So in order to approximate the integral over Hilbert space, I use a collection of quantum states called mutually unbiased bases. Oops, cannot move the mutually unbiased bases. The last word is mutually. So they are a set of d+1 orthogonal bases. So together they contain d times d+1 members when the dimension is 2 to the n. And a property of the mutually unbiased bases is that the members spread evenly over the Hilbert space. So the fidelity will be either 0, 1, or 1 over d. And also a famous property is that the MUV is a complex projected true design. So we can we have this equation. So the integral over Hilbert space can be computed by the sum. I'm sorry, I forgot the sum. Okay, sum over k from 1 to d to the dk. So we use this one to approximate the last one. It's not exactly the same, but yeah, numerically show that the effect, the integral and the sum is similar, is close together. And finding NUVs for the space dimension should be narrowed down to algebra on the Galois ring for n. So grasping everything together, we define the shape distance like this. So it's a minimization over V, the matching unitary, and every 5k. 5k is the corresponding state to psi k. And we collect every 5k together into a matrix, and so M is a matrix that every column contains 5k. Every column of M is 5k. But it turns out that the optimization is not easy to solve. It is equivalent to this problem, to solving a dynamic problem between a probe system and an environment. And we haven't found a proper way to solve that. But we can solve when there is no power true for the fidelity term. This is solvable. And we decided to choose it as the shape distance. This one has several good geometrical properties. For example, it is a metric. That is, it satisfies the symmetricity, the triangle inequality, and the identity of indiscernible. And the shape distance is can capture when the two have exactly the same shape. That is, when the shape distance is 0, then the integral over the entire universe is also 0. And so the gate type mismatch is the distance between two types of gate. The next one, we have to consider the difference in terms of position the gate have in the respective quantum natural network. Here we can view the topology of a network by using a graph, a DIG graph. So DIG is so directed acyclic graph. From here, suppose we have the gate UI of the first network and the gate Bj from the second network. We define the structural difference by the sum of distance between the gate to each of the starting point and each of the end point in the circuit. So it's the difference between every term like that. So when the two gates have exactly the same relative position in their circuit, so the structural similarity will be 0. And finally, those are 3 ingredients to define the distance between two networks. So in order to make the distance, we generalize we use a tool called optimal transport distance. So the optimal transport distance is another optimization problem here. And before we come to this one, I want to explain briefly about the optimal transport. So suppose we have a lot of suppliers and we have a lot of destinations. We want to transport goods from the supplier from the storage to the destination. Suppose we have the total amount of goods the supplier had equal to the capacity of the destination, and we have the ground distance, that is the distance between, for example, distance between every supply, every storage and the destination. We want to find a route and a transport plan that minimizes the total distance we have to transport goods. So, and the problem is expressed by the optimization problem here. The Z is the matrix that term Gij is the amount of goods you will transport from the supply I to the destination J, and the cost function, the same thing. The cost function Cij is the ground distance between the two nodes. This also satisfies to some condition. The conditions are trivial. So by defining the cost matrix as using the ingredients you had before, like the gate type mismatch plus the structural disparity, we have a force matrix here. And solving the linear programming problem, we have the optimal transport distance. And it can be solved, it can be proved that the optimal transport distance is indeed a metric. So until now we have two metrics, one in terms of gate, another one, this one in terms of architecture. And we put everything together, the covariance, the kernel function into the Gaussian process, and we use expected improvement to maximize the we maximize the expected improvement. Then we use that to find good architectures for the following problems. We have three experiments. The first one is to simulate a quantum Fourier transform. The second one is to solve the MaxCut problem, and the last one is to find a quantum generator for the problem of quantum generated adversarial network.
What does trials stand for?
Trials are, so we run this experiment several times and get the mean. So the trial is just.
But what do you change?
No, not changing.
Okay.
Just a new randomization. Okay. So in every case, the expected improvement with Bayesian optimization achieves the best performance. So here, in some special instance, like the algorithm finds out a shortest architecture than the Qiskit offer. Then the Qiskit, is, you know Qiskit, right? Yeah. For example, in the 2-qubit state, then the QFT in Qiskit used 7 gates, but we found a lot of 6-gate architecture that can perform QFT to the perfect precision. So fidelity is 1. This is a little bit surprising that the Bayesian optimization can outperform the MaxCut answers in terms of the MaxCut problem. Probably because we have for the MaxCut problem we use up to 9 qubits and a total of 10 graphs, so 10 weighted graphs, and we the architecture, there is only one architecture have to solve the entire 10 MaxCut problem and summing to the average together.
So what is the MaxCut answer?
The MaxCut problem was proposed in 2014, and the answers was a kind of a quantum annealing. It's a characterization of a quantum annealing. So
QAOA.
Yeah, QAOA. Exactly.
Okay.
Yeah.
So easy Getty paper.
Yeah, it's a Fourier paper. Probably because the number of qubits is too high and the weighted graph is very complicated. So if you the depth of 3 is not enough for the MaxCut problem to solve it. Yeah, that surprised me a little bit. Yeah. And these are the optimal architectures we found for the experiment. Right. Thank you for listening.
Thank you.
Question?
Well, maybe you can go back to the theorem for optimal transport. Yeah.
Optimal transport.
Yeah, like this one. Yeah. Okay. Yeah. So 18 is an NP, no? It's simple to see that 18 is a linear program. And then I haven't finished reading the rest. What is L1?
Where?
L1? No. The amount of mass of UI in L1.
Yeah, L1 is the set of aggregate in the first neural network, and L2 is aggregate in the second neural network.
Wow.
It's basically the same as G1 and G2. But in the paper, we specify a little bit clearer, so we change the notation.
Can you come back a few slides earlier when you introduced like the three metrics altogether? Yeah, the first one when you put that side by side. Yes, this one. So each of the three metrics that we introduced. So just to make sure I understand here, the big thing is that you use them in parallel to assess like the quantity of the architecture that you currently have. Is there some kind of weighted average between the two, the distance that you evaluate when you choose a specific architecture but compared to those measures? What kind of like in the results you presented, which were the metrics that were minimized the most, I would say, because if you try to account for all those metrics all together, obviously there's going to be some discrepancies, right, between the gauge mask or stretching that.
Yeah, the come from the top. The top layer. So the top layer is the Bayesian optimization, right? And it requires the distance between two neural networks. And the distance between two neural networks is a optimal transport distance. So the optimal transport distance can be constructed from the ground distance. And in this case, the ground distance is the distance between every pair of gates in two neural networks. And yeah, the distance between every pair of gates can be built from the gate type mismatch and the structural similarity. And for the where is it? Yeah. For the macro layer, the Bayesian optimization. Here, for every iteration, we sample a new architecture from the fitted Gaussian process. And if we found a new architecture here, we can learn it. We can fit the parameter. We can train the architecture, and the performance after training will be assigned as a next point the next point into the data set. So the data set will append will contain a new architecture as well as the new performance of the architecture.
What is the starting set of training data?
I used five random architectures.
Five random?
Yes, just five. Five architectures, train them, and get the training set. So from the 6th point, we use this process.
Is the training process expensive? How long is the training process? They take decades to get a good architecture.
No, it's just like a few, it's about train.
Or maybe compare it against like the
25 iterations.
35 iterations.
the first iteration shouldn't take long because most of the time the cost of computation is about fitting the Gaussian process. So the distance things takes little time to compute. So it's efficient for the distance between architectures, but fitting the Gaussian process takes more time. And yeah, most of the time it's around after iteration 15. Yeah, fitting the Gaussian process is a bit expensive. Yeah.
How is the training process scale with the number of qubits, like ratio efficient for large system size?
Yeah, that's a problem. And to be honest, I'm not really sure about when scaling the system, how it will go, because as you see in this one, I choose not cherry picking, but I choose the setting so that the number of total possible positions for the gate will be less than 50, because Bayesian optimization will be most efficient when for not for a very large number of parameters, So if the limitation of this work is that it's not really scalable because the problem with Bayesian optimization.
So by parameters is the number of keys in your system. In your system. What is the
Parameters.
Yeah.
The parameters are, let's see, I have another representation in the matrix form. With that representation, you may see the number of parameters for the architectures much clearer. For example, a X here, the first gate in the circuit can be either in 1, 2, 3, 4 position, and can yeah.
I see the deeper the circuit and the more parameters they have, and the other ways that the more qubit they have, the more parameters they have.
Yeah, it scales very fast.
So like even for a constant number of qubits, like for example, it's 4 qubits, the circuit depth is very deep, then your circuit might have a hard time to do the optimization. Is it correct?
The optimization on the circuit it should not take a lot of time. The problem is with Gaussian process as well.
Yeah, because you have to do trainings on the based on using the Bayesian process, right?
Yeah.
Okay.
So just to make sure I understand, the Gaussian process helps you pick an architecture, right? And then like which is regardless of the values of the parameters. Then for each architecture, you will try to optimize the parameters and assess. And okay, so now the question is the distance that you want to assess through your MaxCut, the cost function you're trying to minimize in this case. You wait for picking the best set of angles for each of those parameterizations before shifting to the other one, or because you see each parameter you could try to find the optimal value, right? Like which for your MaxCut, like the ratio. So this is what you do. You try to find the optimal set of parameters for each architecture, and then you compare them together.
Yeah, they are all the best optimal parameters for every architecture.
And how do you know you're not in a local minimum?
Yeah, I tried several times. Several times with different initializations. It's about if I'm not wrong, then I train it. Each architecture I train 5 times at least. QGAN I train just 5 times because it takes a lot of time. More time, not really a lot, but more time. But QFT and MaxCut at least 10 times. And yeah,
like for Q, yeah, as in now just a bit more related to the data set, because like for QGAN, you need some data sets, right? So what are the data sets that you use to train?
Yeah.
And we'll do the different type of data set affect the performance.
Yeah, okay. I forgot to tell to describe the Q-gun. The Q-gun, the goal is to generate a even mixture of two normal distributions. So it has to mix up, here, down, up. So it's a binomial, no, not binomial, a normal distribution with two peaks. I can say that.
Okay.
So now that's the training data for the Q-guns. And yeah, that's the most complicated data set I tried. For all the distribution, yeah, it's even got a lot of zero between.
Oh.
I think if there are no other questions, thank the speaker again.